Hey folks, curious how to predict house prices with Python? Well, join me as we build a regression model from start to finish. I'll share insights from my experience as an industry engineer and data scientist, highlighting not just the how, but also the why behind each step. And along the way, we'll explore the business impact and value beyond just the code. Let's dive in. In data science, we typically start with a business problem. The general goal is to build a predictive model to help you or your firm do something better, faster, or cheaper. Understanding the business goals ensures that you build something that's fit for purpose and optimized for the right metrics. Plus, the funding for your project often comes from the area you're delivering value to, so you need to understand their needs. Now imagine you work for an REIT, which stands for a Real Estate Investment Trust. It's a type of company that buys, holds, and sells a lot of real estate. In a nutshell, REITs allow people to invest in real estate without buying actual property. Now, since they trade large volumes of real estate, they need a consistent and accurate way to appraise or value properties. Now, with traditional appraisals between two professionals varying up to a whopping 40% for the same property, the question is, can we train a machine learning model to help our hypothetical REIT firm predict real estate prices accurately and consistently? That's the business problem we're going to tackle. We'll build our machine learning model by following a streamlined data science process with 7 key steps. Step 1, understand the business requirements. We're talking about that right now. Number 2, exploratory data analysis, EDA. Here, we'll dive into the data to understand its structure and uncover patterns. Number 3, data cleaning, where we process the data to ensure that it's in the right format for our machine learning algorithms to chew on and learn from. Number 4, feature engineering. We'll create new features to improve the performance of our algorithms, helping them extract the signal from the noise. So these 3 steps, EDA, data cleaning, and feature engineering, they're often collectively called data discovery. Number 5, modeling, where we're going to fit various algorithms to our data. Number 6, evaluation. We'll assess the performance of our models and identify the best one. And finally, step 7, deployment. We'll deliver our winning model to business stakeholders for them to use. Now, for small projects, a data scientist can pretty much handle everything end to end. In larger projects, however, you'll collaborate with data engineers, the data plumbers of the firm, and with machine learning engineers who will help you deploy and maintain your models in a production IT environment. See my blog for more details. Now, to showcase our end-to-end data science process, we'll use Jupyter Notebooks, the bread and butter tool for data scientists to explore data and prototype models quickly. Data science is an iterative process, so a notebook's flexibility that allows you to fail fast and break things is ideal. To train our model, we're using a dataset of 1,863 properties from a hypothetical REIT, which I got from elitedatascience.com. It's a great dataset to showcase the whole data science process. Now, since our dataset is labeled, we're performing what's called supervised learning. And because we're predicting a numerical target variable, that is the price of real estate property, given a bunch of features about it, this is what's called a regression task. In contrast, classification tasks predict categorical variables, which I've covered elsewhere on this channel. After training our best model, we'll deliver 3 things to our business stakeholders, the property appraisers inside our hypothetical REIT firm. We'll give them, number 1, the winning model. They'll certainly need that. Number 2, we'll give them some handy Python scripts to process new data, making it ready for scoring. And number 3, a list of feature importances to understand which factors most influence property prices. All right, let's dive into our exploratory data analysis, EDA. This is where we get a feel for our data, which will help us clean it in the next step and engineer some features afterwards. First, we import our Python packages. There's pandas for data manipulation, NumPy for numerical computing, and matplotlib and seaborn for plotting visualizations. These are some bread and butter Python tools for data science. We'll also use various modules from scikit-learn, Python's go-to library for machine learning, to train and evaluate our models. Lastly, here's some code to customize our notebook's behavior. Alright, next, we're going to read our dataset into our notebook as a pandas data frame. This allows us to view structured data like we would in Excel. Here, you might want to spend just a few minutes poking around, examining the dataset, noting what features we have, noting any obvious data quality issues, and of course identifying our target variable. If you need detailed information on what any column means, use the data dictionary for the table. In any company that treats its data assets seriously, you'll have good data dictionaries to understand the fields of a table and also tools to visualize their data lineage. Now, we have nearly 1900 observations for our hypothetical REIT firm, detailing various attributes about each real estate property. This includes transactional information like the property price, which is our target variable. There's transaction dates. There's property type, whether it's an apartment or a house. The number of bedrooms, bathrooms, the size of the total property, the size of just the buildings themselves, the built-up livable areas, and materials used for its construction. There's also information on neighborhood amenities like nearby restaurants, shops and schools, and some demographic data. Next, I've written some code to display all the features of our dataset, their types, either categorical or numerical, and which features have missing values, which we'll have to clean up later. Let's dive into our numerical features, starting with calculating their descriptive statistics and plotting some histograms. This gives us insights into the average, smallest, and largest values of our numerical features. Visually see their distributions and spot potential outliers. For example, our target variable, which is real estate prices, is right skewed, which isn't particularly surprising given that we're dealing with real estate. Now, prices range from $200,000 to $800,000 in this dataset, with a median of $392,000. Using seaborn, we can make a violin plot to gain an even richer picture of the distribution. Looking at the year of the last transaction, we see a bimodal distribution with peaks around 2005 and 2013. Now, these correspond to periods of high activity in the US housing market due to the housing bubble and the subsequent recovery after the global financial crisis. For the square feet and lot size features, now both are right skewed, but lot size is extremely right skewed. The violin plots clearly show outliers, with some properties having vast land areas. The largest estate is a whopping 1.2 million square feet. Now that's equivalent to 27 acres, or 21 football fields, or 12 entire city blocks. We'll remove this outlier during data cleaning as it may add noise to our model. The basement feature shows all homes have, well, one basement, which is very interesting. But as it turns out, 226 rows have missing values here, likely indicating that those properties have no basement. We'll address this during data cleaning. Finally, we plot a correlation heat map to identify strongly correlated features. This is known as multicollinearity. For example, restaurants correlate strongly with nightlife and cafes, and property tax correlates strongly with insurance costs. This helps us later during feature selection because we will want to remove highly correlated features from our final dataset to prevent training issues that can make our results less reliable. This includes the possibility of what's called unstable coefficients for linear regression models. So that's our numerical features. Diving into our categorical features, we've got 3 of them. There's property type, which broadly speaking segments all properties into either apartments or freestanding houses. Then there's exterior walls and roof, which refer to the materials used for the walls and roof of each property. We note that both these features have sparse classes with hardly any observations in them. There are also some data inconsistency as well, with the composition class appearing twice, one with uppercase letters. Both these problems can interfere with our model training, so we'll clean them up later. So that's our categorical features. To drill deeper in our data analysis, we can combine numerical and categorical features using aggregations and segmentations. For aggregations, we can group properties by their type, either apartment or a house, and calculate the average price, the average lot size, average number of bedrooms, and so on, to understand how all these features differ between apartments and houses. We can then get even more detailed with segmentations. For example, by segmenting our data into their property types, we can make 2 box plots for real estate prices, one for apartments and one for houses. So now we can visually compare the entire distributions of property prices between apartments and houses. Here, we can see that apartments are generally cheaper than houses, not terribly surprising, although there are certainly some very expensive apartments as well. Cool, that's enough EDA for now. While you could spend days exploring your data, as a practicing data scientist, you do want to time box your EDA to meet project deadlines. I'd say use the 80-20 Pareto principle. Once you've got a good feel for your data, you've spotted some major issues, and maybe you've got a few good ideas for feature engineering, it's time to move on to the data cleaning. The first thing we're going to do is drop unwanted data. This includes duplicates, which we don't have for this dataset. Fantastic. We also don't want unhelpful outliers that might cause our model to overfit. For example, I've removed that absolute monster of an estate that's 1.2 million square feet. Next, I want to fix some structural issues with our data. This includes what's called implicit zero imputation, where missing data, the nans, actually mean 0. For example, our basement feature has 1, meaning, yes, this property has a basement, and the nans actually meaning no basement. So I replace all the nans with zeros, creating a proper indicator variable for the basement feature, now with 1s and 0s. Data quality is also a structural issue. This includes data inconsistency, incorrect data types, and wrong values. In our roof feature, we have an inconsistency where composition and composition, with a capital C, are really the same thing. So why not combine these classes together? The final structural issue is sparse classes in our categorical features, a problem plaguing our exterior wall and roof features. Here, we're breaking down materials into too many classes with very few real estate properties falling under some of them. So let's combine some of these classes, resulting in fewer but bigger classes. For exterior walls, we now have wood, brick veneer, aluminium and vinyl, metal, combination, and a catch-all others class. Just 7 classes in total now. For roof materials, we have composition shingles, shake shingles, asphalt, and an other catch-all class. Just 4 classes now. Nice. Next, let's fix our missing data issues. Here, we'll either impute the missing values with something else, or remove the missing data altogether. We have 2 features with missing data. 223 properties with an unknown exterior wall material, and 353 properties with an unknown roof material. Now there's no need to delete these rows. There's information for all the other features. Plus, these rows in total represent a whopping 30% of all our data. We'd lose a lot of good data through removal. Instead, we'll create a new class called missing that allows us to preserve all this data. Now, next up, we need to convert our categorical features into numerical values. This is an important part of data preparation. Some algorithms like linear and logistic regression can't work directly with categorical data. They need numbers for calculating things like distances and gradients. The easiest way to address all of this is to what's called one-hot encode our 3 categorical features: exterior walls, roof, and property type, which we can do with just a single line of code using Panda's getDummies function. This creates a brand new indicator variable for every class in these 3 features. So now we have numbers indicating when a property has a certain attribute. For example, a property with brick walls will now have a new numerical feature called exterior walls underscore brick flagged as 1. Lastly, let's remove any highly correlated features to reduce redundancy and prevent potential issues during model training. This is called dealing with multicollinearity. One of the potential problems is what's called unstable coefficients. For example, there's a high correlation of 0.98, very high, between property tax and insurance, including both features as part of the data we feed into our algorithms might make the optimization process unstable, with a model struggling to attribute the effect on the target variable to one of these features over the other one. This leads to large swings in the model parameters during training as you feed new bits of data in, resulting in the final model parameters potentially settling on values that don't quite reflect the true relationship between the two highly correlated features and the price of the property. Ultimately, this messes with our model results and, even worse, corrupts the list of feature importances. We have restaurants, nightlife, and cafes all highly correlated, with an R value greater than 0.9. So I'll remove nightlife and cafes, but keep restaurants. I've also removed property tax and kept insurance. A general rule is, if you want to be conservative, correlations stronger than 0.8 qualifies for feature removal. So looking at our heat map, that would mean removing this whole pocket of features here, leaving just one. For example, retaining the restaurant feature to serve as a representative feature for all of these other amenity features. Cool, that completes our data cleaning discovery work. It's a good idea now to save our clean data frame at this point. We've now reached feature engineering, my favorite part of the entire data science process. This is where you get to be creative, leveraging insights from data cleaning and any domain knowledge you might have to craft new features from existing ones. These new features can help your model learn better, reduce overfitting, and ultimately improve performance. They also enhance model interpretability by making it easier to explain your results. By massaging your data into the right form, you can really enhance your model's ability to learn patterns, which means more accurate predictions. Good feature engineering can be that secret sauce that draws out the most from your data. You can spend days engineering new features, but for this project, I'm going to engineer just 4 and see how we go. First, let's create a feature called property age, which is simply the transaction year of the property minus the year it was built. It makes sense that, hey, how old a property is influences its price, right? Next, I'll create an interaction feature called school score, which will be the number of schools multiplied by the average quality of those schools. Now, this is a way to express the amount of quality education available in the area. If schools turn out to be influential for our model, this feature might be a better representation than just the number of schools or their average quality alone. Then, I'll create a feature called 2 and 2 that captures when we have 2 bedrooms and 2 bathrooms. This is where, as a data scientist, you might leverage your domain knowledge and say, hey, properties with these sorts of attributes tend to be popular for both home occupiers and investors and might have a useful relationship with the price of the property. Finally, we'll make a feature called during recession, which indicates that a property was sold between 2010 and 2013, which is during the recession period after the global financial crisis. A data scientist with domain knowledge in real estate, economics, and financial markets might have insights that a feature like this would play an important role in determining house prices. Cool. I then dropped the year built feature, since it's almost perfectly captured by our new property age feature, as shown in our updated correlation heat map. Cool. We've just made 4 new features, and we can come back later to engineer more if needed. Generally, I like to classify feature engineering techniques into 7 categories. Number 1, transformations. So that's adding, subtracting, multiplying, or dividing features. Our property age feature falls here. Number 2, aggregations. So grouping data and calculating statistical measures. For example, grouping customers and then calculating their average spend. Number 3, Boolean transformations. So that's creating features based on conditions. Our 2 and 2 feature, 2 bedrooms, 2 bathrooms, is an example. Number 4, binning or discretization, converting numerical features into categories. Our during recession feature is actually an example here. Number 5, encoding. So that's converting categorical features into numerical values, like label encoding and one-hot encoding, which we actually did during data cleaning earlier. Number 6, time-based features. An example being lag features. For example, features like last month's mortgage rates or last quarter's economic performance. And finally, number 7, interaction features. So that's when you multiply features together to capture complex relationships, like our school score feature. Finally, I saved our analytical base table, which is our completely clean dataset with our 4 engineered features on top. The ABT is our raw dataset that's now cooked and ready for our machine learning models to munch on. Great, now we finally dive into the modeling phase. Hooray! Where we're going to fit a range of regression models to our data. Now, thanks to our diligent efforts cleaning our data and engineering new features, we can hopefully train some good models that can learn the signal from the noise and keep overfitting at bay, meaning it can generalize well to new unseen data and make accurate real estate predictions. All right, let's go. The first thing we do is write some code to split our dataset, 80% for training and 20% for evaluating the performance of those trained models. I'm going to try out a whole bunch of algorithms, and for each of them, I'll need to configure some hyperparameters. Now, hyperparameters set the overall strategy for how the model will learn from the data, and they're set before training begins. How do we choose them? Well, I'm not going to lie, it's a bit of a dark art. So we set a range for each hyperparameter and use what's called a grid search to cycle through all the different combinations. Now, I'll warn you, like EDA and feature engineering, tuning the model for its optimum hyperparameters that squeeze every last ounce of performance out of your models can become an obsession for some. Moving on, which models are we going to use? Well, it's going to be a nice party because we're going to invite all the usual algorithms for regression. We've got linear regression with 3 types of regularization: lasso, ridge, and elastic net. These methods penalize complexity to prevent overfitting. That's what regularization means. We can tune the strength of these penalties through these alpha hyperparameters, and you can see the big range I've set for them, as I don't quite know what regularization strengths will work the best. Next, we have 3 models based on decision trees: random forest, gradient boosted trees, and XGBoost. Now, a random forest uses multiple decision trees and averages their predictions. Very democratic and robust to overfitting. Gradient boosted trees build trees sequentially, with each new tree correcting the error from the previous one. Pretty cool stuff. Often, they're more accurate than random forests, but they can overfit. Finally, XGBoost is an optimized gradient boosted tree model, well known for its high performance and a lot of podium successes in Kaggle competitions. Our grid search is also training with what's called a 10-fold cross-validation, as indicated by the CV in grid search CV, and the CV equals 10 argument inside the function. Now this means the training set itself is split into 10 parts or folds. For each hyperparameter combo, the model is trained on 9 folds and validated on the final fold. The model is then trained 10 times in total, with each fold taking a turn being the validation set. Now, with so many combinations of hyperparameters and each model being trained 10 times, there's going to be a lot of training and validation cycles going on. Now, I'll mention that training with cross-validation isn't necessary, but it often helps tune hyperparameters better. It aids the model to generalize better on unseen data and prevents overfitting. Cool. We've trained a bunch of models, including linear regression with 3 different regularization techniques: lasso, ridge, and elastic net. We also trained 3 types of ensemble decision tree models: random forest, gradient boosted trees, and XGBoost. For each of these 6 models, Grid Search has tuned the optimum hyperparameters. And during the model training process, each of these models were fit to the data, adjusting their internal model parameters as it learns patterns. Now think of these model parameters as kind of like knobs and dials that continuously turn as the model munches on juicy data, being fed in batches at a time. By the end of the training process, each model has learned what their model parameters should be, with the knobs and dials eventually setting into place after consuming all the data. Now, we just need to assess the performance of these 6 models and decide on the winning model overall. And we're going to use 3 common regression metrics to help us do that. R-squared. This tells us how much of the variation in house prices can be explained by our model's features. There's the mean absolute error, MAE. That tells us on average how much our predictions are off by. And finally, mean squared error, MSE. This highlights how big the model's mistakes are by squaring the errors, making them stand out more. Now, comparing the performance of our 6 models with their tuned hyperparameters, we can see that our 3 decision tree models performed significantly better than our linear regression models. Our best model overall was the XGBoost. For R-squared, 78% of the variation in house prices can be explained by the features in our model. Now that makes the model almost excellent, but not quite there. For the mean absolute error, our predictions are off by an average $49,000. That's not bad. Generally, you want the MAE to be within 10% of the range of your target variable. Now, the properties in our dataset have a $600,000 price range difference, right, between $200,000 and $800,000. So being off by less than an average of $60,000 means we're doing okay. And finally, the large MSE indicates that there are some predictions with some very large errors, right, heavily penalized by the squaring process. So all up, our model isn't fantastic, but hey, it's not too shabby either. Let's check out our feature importances. This chart ranks our features based on their relative contribution to the model's predictions. Now here we can see that insurance and the year of the sale and the size of the buildings and livable areas within a property, these 3 features have the strongest relationships with the price of the property. A word of caution, however, be careful how you interpret and communicate these relationships to your business stakeholders. Feature importances don't imply causation, and they also don't tell you the direction or nature of these relationships. From this graph alone, I can't say that a higher insurance price means a higher property price, and I certainly can't say that a higher insurance price causes a higher property price. In fact, using some domain knowledge, I can say that the story is actually closer to the other way around, that higher property valuations cause higher insurance prices. And that's because insurance premiums that people typically pay for real estate is calculated from the value of the property. And that's also how property taxes tend to work as well. So zooming out, it does make a lot of sense that the insurance premium and property tax features are very strongly related to the real estate price, because those things are quite literally calculated from the value of the property. All right, now for a more detailed picture that breaks down our model predictions to show the contribution of each feature, we can look at our SHAP summary plot. Now think of SHAP, which stands for Shapley Additive Explanations, as understanding how much ingredient contributes to the flavor of a dish. Here, we've got all the features running down the y-axis, ordered by feature importance. The x-axis represents the SHAP values, showing the impact of these features measured in the same units as our target variable. So here, that means dollars. The colors represent the value of the features themselves, with red meaning high and blue meaning low. So for insurance, the wide spread of SHAP values on the x-axis shows that this feature significantly affects the model's predictions, up to $100,000 in 2 directions. Diving deeper, we see red dots towards the right. So that means high prices of insurance generally increase the predicted property price, while the blue dots on the left show that lower insurance costs tend to decrease house prices. Pretty interesting plot, isn't it? So that's SHAP. And along with our ranked list of feature importances, we'll be delivering these charts to our REIT appraisals team, who can immediately gain insights on which features of a property are most strongly related to the value of the real estate. Even if they don't end up using our model to score new data, this data science project has already delivered value through identifying potentially important predictors for real estate prices. All right, what are the next steps? You've communicated your model results to your business stakeholders. From here, things typically go three ways. They're not happy with the model, in which case you can go back and try and improve the performance. This might mean sourcing more data or engineering more features. They're fine with the model, but for a variety of reasons, it won't end up being deployed. Or third, they're happy with the model and they want you to deploy it so they can start using it to value new properties. And that brings me to the final step, which is deployment. This is where the real impact of your work comes to life as you deliver your model to your customers and your end users. In this case, we have internal customers, the real estate appraisers and valuers within our REIT company that wants to use our model to accurately value real estate. How do we deliver our model to them? Well, if it's small scale deployment, where an appraiser is comfortable running some Python code on their laptop occasionally, we can provide two things. A pickle file. This is essentially the trained model all packaged up. Some scripts. Now these scripts package our earlier data cleaning and feature engineering efforts into a couple of nice, neat functions. Clean data and engineer features. So when an appraiser needs to use the model and predict a property price, they can first run these two functions to clean the data and engineer the new features just as we did earlier. Then they can input this data into our pickle file, which will score the new data point and output a real estate property price. For a larger scale deployment, where for instance you want to automate the data coming in from different systems across the company and deploy your model on an app that can be accessed online or on a phone, you'll be working with your broader technology teams. Now that includes data engineers, who are the data plumbers of the company. They set up the enterprise-grade data pipelines to feed fresh data into your trained model. You might also work with machine learning engineers, who will take your code from your Python notebooks and refactor everything into performant code deployed in a secure production IT environment, serving customers 24/7 and monitored for model and data drift. Additionally, you might collaborate with software developers who can build the apps and broader software that wraps around your model, enabling ordinary customers to essentially use the AI that you've built. Cool. Well, that's it for this video. Please hit that like button if you found this end-to-end walkthrough for building a simple regression model useful. If you have any feedback, drop a comment. I'd love to hear from you. Check out my blog where I publish a lot of content on AI, machine learning, and enterprise data. In fact, this demo today is based on a project I wrote about a while ago. Shout out to elitedatascience.com for the dataset and their fantastic data science training resources. All right, well, keep learning and growing. Enjoy the process, and I'll see you guys in the next video.